right. Still, oh, come on. Not what I wanted to do. There we go. Still on section 1. We just split it up into 2 days this year. So some more limit of a function of a real variable. So sometimes we saw from yesterday's lesson, sometimes as x approaches a specific x value from the right, which means you're actually traveling left. So from the right means you're coming from the right and you're going left. Or if you're approaching an x value from the left, so if you're coming from the left, it means you're traveling towards the right. The y values don't match, and that's okay. When they don't match, we saw from Mean Girls, right? From the left, it was going to positive infinity, and from the right, it was going to negative infinity. Those two limits didn't match, and so we say the limit did not exist. So it's okay. It's just, sometimes that happens. Here's the notation for it. It's this: as x approaches a, and then this plus sign. The plus sign after the a means that it's from the right. Doesn't mean it's so you could have as x approaches 2 and then a plus sign after it, like up top there. That means from the right. So the limit of f of x as x approaches a from the right is equal to some limit. We're going to call it L. Here's the notation for it approaching from the left. It's as x approaches a, and this minus sign means from the left. It means as you're traveling towards the right, of f of x is equal to m. So if this limit is L and this limit is m, and again, plus sign after the number is from the right, minus sign after the number is from the left, because you could it could be a -2 and then a minus here. It means it's approaching -2 and then from the left. We can have a -2 and then from a plus sign, which means from the right. So if they are the same, if L is equal to M, right, if they are the same limit from the right and from the left, then we just say that it's L. And we say the limit exists at a, and the notation is just that the limit of f of x as x approaches just a is equal to L. So a function may or may not have the same value as the limit at a particular a, and that's okay. The function may or may not have the same value. So asking you what the limit of a function is the y values as you're approaching that value. The function's actual value might be some other number other than the limit, and that's okay. We can still have a limit existing even if the function's value isn't at that same point, and you're going to see that in this. I think it's this next example. Perfect. Yes. Okay. So here's this picture of this graph of, it's definitely a piecewise function, where you've got this straight line here, you've got an open dot there, you've got another straight line with a different slope going that way, and then you actually have a closed dot down here. All right. So we're going to ask you a few questions. This is a very typical question we would ask you. What's the limit as x approaches +2, but from the left? So I imagine, I love roller coasters, and so I imagine being on a ride, and if I'm coming from the left, so here's x is 2, right? And I'm coming from the left, it means I'm traveling towards the right. So you're on this part of the right, and you're going, and as I'm approaching, here's x is 2. What is the y value as you're approaching x equals 2 from the left? Remember, the answer to limit of f of x, blah, 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 is the y value. Your answer is the y value. All right, so from the left, you're on the right. And as you're getting closer and closer to when x is 2, what's your y value? This guy right here, which would be 1, 2, 3, 4. It's 4. All right, even though there's an open dot there, right? The limit as it's approaching 2 from the left is 4. All right, now how about what's the limit as x approaches +2 from the right? So if you're approaching from the right, it means you're traveling left. So you're on this part of the right because you're coming from these x values over here, which are, so you're way up here and you're going down, 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 and you're getting closer and closer to 2. And what is the y value? Oh, it's also 4. Nice. All right, so now what we can claim, if these two values from the left and from the right are the same value, then we actually say the limit as x approaches 2. No longer from the left or from the right, just straight up, what's the limit of this function as x approaches 2? Since these two guys match, it's 4. All right, now, what was that last sentence about the function's value? It may not match. Here's exactly. What's f at 2? What's this function's value when x is 2? Well, there's an open dot here, so it's not 4. It's this closed dot down here. When x is 2, your function is, the y value is 1. So here's one where the function's limit as x approaches 2 is different from the function's value when x is 2. That'll come into play in sections that are coming up. But limit exists because from the left and from the right, they're both the same y value. Let's do another example, similar. Here's from the book. Here's this function where the values that are labeled are not super friendly, but that's okay. Got an open dot here, and it's curving down and approaching this horizontal asymptote, but not actually touching it right there, even though it kind of looks like it. Got an open dot here, and it's coming down over there. And yeah, all right, so let's see what's the first thing they're going to ask us. If this is f of x, yeah, then what's the limit of this function as x approaches negative infinity? So negative infinity is over here in the negative direction. And so as you're going along, you end up being on this part of the graph. And as x approaches negative infinity, you keep going, you keep going, you keep going. What is the y value that it's approaching? Well, it would be this guy right here. If that's 4, then that's 2. Looks like a 1 to me is the y value. Remember, the limit of a function is a y value. How about the limit of this function as x approaches negative 1? All right, it doesn't say from the left or from the right, it's just as it approaches negative 1. Okay, so if this is negative 4, this would be negative 2. So negative 1 is about here, which means right there. Well, if you're coming from the left, you're there, and if you're coming from the right, you're also there. So what is the y value? For when x is negative 1, to me it looks like the y value looks like it would be about negative 3, because that would be negative 2, and that's negative 4. Yep, negative 3. Remember, y value. What's the y value as x is approaching negative 1? How about the limit as x is approaching negative 5 and from the right? So from the right, you're on this guy. So where's negative 5? Well, this would be, there's negative 4, here's negative 6. So negative 5 is this value right here. I'm not a fan of the labeling, but that's okay. As x approaches negative 5 from the right, so you're coming from all these right values, right? So you're probably like, you're on the right, you're going, you're going, you're going. What are the y values getting close to? Positive 4. Now, it's important for me to point out right now that there's an open dot there, right? So your y value isn't actually 4 when x is negative 5 here. It's not equal to, it's not, the function's value is not equal to it because I've got an open dot there. But it's approaching, it's getting closer and closer to that guy. And a nice analogy that I think is if I'm running down the street and I'm running towards home, and then all of a sudden there's an open manhole cover in the ground that I fall through. I didn't make it home, right? But it doesn't change the fact that that's where I was heading. That's where I was running towards home, and I'm almost there, and then whoop, fall through the manhole cover. That would be horrible. But that's how limits are. You don't actually have to arrive there. You just are looking for where were you heading? Where were you almost getting close to before falling through the hole? Okay, so let's look at next one. The limit of this function as x approaches -5 again, but now from the left. So here's this -5 is right here, but you're coming from the left now, meaning towards the right. So you're on this graph here. All right, you fell through the manhole cover, but where were you heading before you fell in? A y value of 7. Nice. All right, so now, of course, the next logical thing that we're going to ask you is, what's the limit as x approaches -5? Not from the left or right this time, just straight up as x approaches -5. So here's this -5, and we found out that from the right it was 4, the limit was 4. Approaching -5 from the left, the limit was 7. These two guys do not match this time. If they matched, then the limit would be that value. But this time they don't match. So what do we say the limit is? It doesn't exist. It does not exist. So we just write DNE for does not exist. Here is a precise formal mathematical definition of a limit using epsilon, and deltas, and it's super confusing. I'm sure you don't have to super stress about it. The limit of a function of f of x is L, so the limit is L. This is the y value. As x approaches a, so here's this a value, denoted by the limit of f of x is as x approaches a is L. If for any positive number epsilon is these little values here, so some teeny little increment, adding or subtracting it to this y value, there is a positive number delta, that's these guys adding or subtracting it. So you're given this like little window such that the distance, the absolute value between f of x and L, f of x minus L, is epsilon whenever the distance between x and a, these guys, is delta. All right. Don't stress about it. It's just, it is the formal one. And when you go into calculus, especially college calculus, you will learn epsilon delta proofs using all of this. It's lovely. All right. Don't let him go off on a tangent. He'll go on forever. Okay. So I hope you all are having a fantabulous day. See ya later. Ta-ta!